Alright, so today we're going to be doing 6.7, which is inverse functions and relations. So an inverse relation is when two relations are inverses, if and only if. If you take AB and you flip the position of A and B, and it gives you BA, that would be the coordinate that corresponds to its inverse. Okay, so inverse coordinates are flipped. Okay, that's the main idea to understand there. In addition to that, when we compose a function and its inverse, when you compose like we did on Friday, both compositions should come out to be x. So do you remember we were checking that on Friday if they came out to be x when we composed them? That's another way you can verify that. Now we also have something called the vertical and horizontal line test. You should be pretty familiar with the vertical line test at this point. It's to check if something is a function if it passes the vertical line test. But in addition to that, you should also familiarize yourself with the horizontal line test. The horizontal line test is basically a test that determines if not only if the function is a function, but if its inverse is also a function. So if some relation exists, okay, if it passes the vertical line test, it's a function. But if it also passes the horizontal line test, its inverse is also a function. So if you go ahead and look at this situation right here, would this function on the left pass the vertical line test?
Yes.
Yes. Would it also pass the horizontal line test?
No. Yes. No. No.
I don't understand the
Yes.
horizontal line.
Yes. How do we yes?
Can you go over that?
Well, that's what I'm about to do now, yeah. So this right here, does this function pass the horizontal line test?
Yes.
No, because it touches more than one point.
Oh.
Okay, so if it touches more than one point on the horizontal, it is not, its inverse is not a function. Yes.
So left one does or does not?
Left one itself passes the vertical line test, so it's a function, but it doesn't pass the horizontal line test, so its inverse is not a function. The one on the left right here, I'm sorry, the one I was right is what I was talking about. The one on the left passes both the vertical and the horizontal, meaning that it is a function and its inverse is also a function.
Wait, so does that like middle part, it just like keeps going down?
Correct.
Okay.
Yeah.
What about that little divot in the one on the left?
That's why it doesn't pass it.
Okay.
Wait, are you talking about the left or the right? Sorry.
The left.
Oh,
that divot where it's straight. Why it doesn't pass the horizontal?
It does pass it. It's just hard to see. Like in reality, if you were to like zoom into this like correctly, this is a cubic function. It actually isn't perfectly straight. It's just like we're seeing it from far away, so it looks more straight. Does that make sense?
Yeah.
Okay. Sorry, I was just testing my microphone.
So this passes.
Yes. All right. So, first thing we're going to do is we're going to just analyze this process, and we're going to kind of look at these to determine what an inverse looks like. Okay. So first and foremost, as you can see, I've already graphed the line y equals x. So we know that inverses of relations will be reflected over that line. So we're going to start by graphing this table right here. So you're going to go ahead and plot those points. And you should end up with something that looks like this. And you can connect them if you want. Now what we're going to do is we're going to find the inverse. So when we have a table and we want to find the inverse of that table, all you have to do is flip the x's and the y's. So that's how you would find the inverse table. You just flip the x's and the y's. And now we're going to graph that one as well. And you're going to connect them. And what you should see is that these are reflections over that line y equals x. So does everybody see how that they are reflections over that line? So every time you graph a function and its inverse, it will look like that. It will be a reflection over the line y equals x. So that's why, if you have to do this on a test or quiz, I would recommend drawing that line in and making sure it looks like it's a reflection over that line to verify you did the math correctly. All right. So now we're going to learn about how we can find inverses algebraically as well. So step one is let's go ahead and find that inverse. So here's the way that you find the inverse algebraically. You start with whatever function you're given. That function, if it's given with y equals, you can start right away. if it's given with like f of x or g of x, you're going to replace that with y and then proceed, okay? So on the homework, they might have f of x, g of x. Make sure you replace that with y first. Next step to find the inverse is to simply switch the position of x and y. I took the function, I rewrote it, but I switched x and y. Is everybody with me so far? Okay. Now from here, I want to solve for my new y, okay? So to do that, I'm going to subtract 4 on both sides. That's going to give me 1x minus 4 equals 3y. And then what would be the next step to get y by itself? Divide by 3. So I have to divide each term over here by 3. And that's going to give me y equals 1/3 x minus 4/3. So does anyone have any questions about how I got that? Yes.
Why is negative 3, why not negative 8?
Wait, what?
Wait, with negative 3y, but then below it with positive 1.
Oh, you're right. I forgot to divide by a negative. Thank you about. Sorry, I thought you said 8. I was like, what? Sorry, these are all opposite signs. My bad. I literally was like, oh, I gotta make sure I do divide by a negative, and then I totally forgot. So thank you for that. It should have been the opposite. Does anyone have any other questions about that? So when you go to write the notation for the inverse, since they both are y equals, here's how you denote the difference. You put y, you put this negative 1 on it, and that indicates you're talking about the inverse, okay? So now that we have the function and the function's inverse, we're going to go ahead and graph both of these. I'm going to have to zoom out because I don't have a ton of room here, so you've got to bear with me. You guys can move up if you need to see it better. It's fine. All right. I tried to make it a little bigger. So we're going to go ahead and graph this original function. I'm going to go ahead and graph the original in purple. I'm sorry, in blue. How can I rearrange this so it's in the form y equals mx plus b? Good. It's going to be y equals negative 3x plus 4. So the reason you have to do that is because that's the way we're in the format of which we can graph something, right? So from here, I'm then going to start at my y-intercept, which is at 4. And then I'm going to go down how many?
3.
And over? Good. Down 3 over 1. And you're going to do that a couple of times, as many as you can until you run out of space, okay? And you should end up with a line that looks something like this, and then at this point you can just connect it like that. So get it to look the best you can. And now we're going to go ahead and graph the inverse as well. So the y-intercept of the inverse is 4/3, which is 1 and 1/3, right? So 1 and 1/3 is like about here. I'm going to go down 1 from there, my y-intercept, down 1 over 1, 2, 3. Does anyone know what you can do if you run out of room going to the right? Opposite to left, good. Up 1, 1, 2, 3. Once you have that, you're going to connect it like this. So now it's always a good idea to visually confirm that they look like they're inverses. So I like to draw the line in, just roughly. Do they look like they're reflected over that teal line there? Yeah, they've been reflected over that line. So we've verified that they look like they're inverses. So now our goal, yes, go ahead.
How did you get the teal line?
Oh, it's just the line, always the line y equals x, which is just a y-intercept of 0 and then up 1 over 1.
Alright.
You're welcome. Okay, so yes, go ahead.
How do you get the starting point for the second line that you drew?
Oh, it's just the y-intercept, which is at 4/3, which is 1 and 1/3. You can always do it in the calculator to get a decimal and do it that way as well. So the original function, the one in the blue, what would be the domain of this function? Good. All linear equations have that domain, and they also have that as their range, right? It's going to go to the left, up, down, and left, and right forever, okay? All the directions, because it's linear. Is the original one in the blue, is that a function? Does it pass the vertical line test?
Yes.
Does it also pass the horizontal line test? Yes, which means that the inverse is also a function. Now you can also see that visually here with the inverse, but you could have determined it before you graphed it as well. The inverse. So when you go to do the domain of the inverse, domain and range are just gonna flip. You see that? So in this case, they're just gonna stay the same because they were already the same to begin with. But when you go to do the inverse, the domain and range always flip. Okay? So any questions about that? Yeah, go ahead.
Do you mean the range is the domain and domain is range?
Correct.
Okay.
Yes. Yes, the domain becomes the new range, the range becomes a new domain. Yep.
Wait, so what's different with those two equations? Like,
There's nothing.
There isn't anything different, which is why the domain and range look the same for both of them, since they already had the same domain and range to begin with.
8.
Does that make sense?
Will that always happen?
No. Sometimes they're going to be
So
different.
sometimes it will actually flip.
Correct. You're going to see examples of that for sure today. All right, so you guys ready to try another one?
No.
So, do you all remember how to graph the line y equals 2?
No.
Horizontal line, right?
No.
It's just a horizontal line through the value of 2. Because all you have is a y-intercept, right? So when you only have a y-intercept, the slope must be what? 0. So that's how you would graph this. Okay. So we have the first one graphed. Now, does this function pass the vertical line test?
Yes.
Does it pass the horizontal line test?
No.
No. Now we're going to go and find its inverse. To find the inverse, we flip the x and the y. So if I'm flipping the x and the y, there's only one thing to flip, right? The y is going to become an... And there's no y to solve for, right? So we can't do anything with this, but we can graph it. Does anyone remember what this looks like on the graph? Vertical line like this. Good. So we found our function and we found our inverse, and now we're going to find domain and ranges of each. So for the original function, the one in the blue, what is the domain?
Negative infinity to infinity.
Good, negative infinity to positive infinity. What about the range?
0.
It has one value in the range. 2. So when you only have a single value, you put it in the little squiggly brackets, okay? Now, to find the inverses domain and range, you could just flip them, but let's just actually think through it as well. What would be the domain of the function in the purple? 2, because it only ever takes on a single x value of 2, right? But what about its y values? Yeah, so you see how it does end up taking on the opposite of the original?
Yeah,
And is the inverse a function? No, because it doesn't pass the vertical line test, right? So any questions about that one?
No. Is this how it will look on the quiz and the test?
I mean, yeah, more so. I mean, of course, you're not going to be graphing, but questions about it. Yeah.
Wait, so what is the horizontal line test prove?
The horizontal line test can tell you before you graph the inverse if it's going to be a function or not.
Oh, okay, so.
So once you have it already graphed, it's kind of pointless, but yeah.
Okay.
And just to clarify that, you could have a question where you would graph, but obviously you know how the quizzes are. They're more guided than this usually.
Yeah.
Okay. So this one here, let me make this a little bigger. So you're going to notice these questions have tables. We're going to go ahead and graph it both ways. We're going to graph it with the table, but we also need to find the inverse. So step 1 is, let's go ahead and graph that original function. Can anybody tell me what function family this belongs to? Quadratic. Do you all remember, don't graph this, what a quadratic parent function looks like? It's a parabola. So this parabola has a original vertex of 0, 0, but it's been shifted down how many units? So we know that it starts when x is at 0, if I plug 0 in, that's going to give me a y value of -5, right? And that's going to be like essentially my vertex. So how can I find some other values on the table? Good. And good. And now I just have to plug these in, but I know these are going to match, right? So if I plug in -1, what's -1 squared? -5? -4. This is also -4. You can test it if you don't believe me. What's 1 squared? I'm sorry, 2 squared. 4 minus 5? So this is also -1. So we can go ahead and graph this over here. And you should end up with something that looks similar to this. Now, to find our, before we do that, I guess, let's go in order. Does this function pass the horizontal line test? No. So we know that its inverse is not going to be a function, right? So let's go ahead and find the inverse equation. You're going to start by flipping the x and the y. So it's going to be x equals y squared minus 5. So you see how the x became a y and the y became an x? Now our goal is to solve for the new y. So that's going to become y squared equals x plus 5. And then how do we get rid of a square in math? It's good, we square root. Now if we square root something, we have to put in a plus or minus. So this actually ends up breaking up into two equations. Y equals negative square root x plus 5 and y equals regular square root of x plus 5. So I'm going to talk a little bit about how and why it breaks up and how that affects us. But before we do any of that, do we need this inverse? Now that we have a table, do we need the inverse to graph the inverse? No. What can we do with the table? Flip it. So you can always use the inverse to graph the inverse, but if you have a table, that's an even easier way to approach it. So now that we've flipped our table, we're going to go ahead and graph our inverse, which is not a function, but that's okay. And you should end up with something like this. So as you can see, they are inverses of each other. And let's identify domain and range. So what is the domain of the original function? Good, because it's going to get wider and wider as time goes on. What would be the range of that function? Good, -5 to positive infinity. Now, what about the inverse relation? What would be its domain? Good. We know that because they flip, but also you can see it, right? And then what about its range? All real numbers, because this one gets wider this way, taller and downward, okay? So, is the inverse a function? No. So let's look quickly at something on Desmos real quick. Alright, so as you can see here, I graphed the original function. I graphed the left piece, or the below piece, and the above piece. See how I have the negative and the positive one in here? You have to graph it as two separate pieces. You see how these pieces together combined make that relation? That's because anything that you graph that's not a function has to be graphed as two pieces that are a function. So if we looked at each of these pieces stand alone, are they each separately functions? Yeah, if they were without the other piece, they would pass the vertical line test, right? So that's why we break it up into two pieces. So now I have two pieces that are functions. So we adapt to kind of work with it that way. So you'll notice that square root function is essentially the inverse of the quadratic function, but it's like a piece of it that makes it a function, and take away the piece that makes it not a function. So just something to think about. Alright, so as for the other one here, the next one, first thing I want to do is identify what function family this belongs to. Quadratic. And it has a vertex of what?
2.
1, 2. Do you guys remember that?
No. Oh, yes.
Yes, good. So, in case you forgot, I'll kind of refresh your memory real quick. Whatever the value on the x's is going to flip, and then the h and k, okay, it flips, if you remember that. So, do you remember how to find the rest of the table?
Oh, if you hit N, never mind.
You're right, you do. You're on the next step, though. So, you're going to take those values and plug them into the function, right? So, what is 0 minus 1? Negative 1. What's negative 1 squared? What's 1 plus 2?
3.
So we get 3 here and 3 here.
Wouldn't the graphing calculator give us this?
It could, but you're not always going to have that, you know?
Why
So
not?
what do you mean why? Because you don't get it on certain tests and stuff like that.
But why? Is there like a reason?
Yeah, in college, a lot of colleges don't let you use calculators. Mine didn't.
That's so weird.
So what would be 3 minus 1?
2.
What's 2 squared? 4 plus 2? 6. All right, so now you're going to graph this. Now, only 3 of these values in the table are going to actually fit on your graph. That's okay. So we're going to get 1, 2, 2, 3, and 0, 3. Looks something like this. Now we're going to identify this as a function or not a function. What do you guys think?
Function.
It is a function, but its inverse will not be a function, right? Okay. So we have to find the inverse, so we're going to switch the x and the y. We're going to solve for the new y, so I got to get the 2 over here.
Can't we just switch it in the graph?
You can, but the question also wants us to find the inverse function. So we have to actually find that actual function as well, not just the graph of it. So I square root both sides. That gives me plus or minus the square root of x minus 2 equals y minus 1. And then what would be my last step to get the y by itself?
Plus 1.
Good. Plus 1. All right, we get y inverse equals 1 plus or minus the square root of x minus 2. So, now that we have the inverse function, we can find the graph of it easily by just flipping the x and the y. So you're going to notice a lot of times you can do this to get the inverse, but you have to be careful because sometimes the question still wants you to find the actual inverse itself. So you can't always just do the graph part. It's going to look something like this. What would be the domain of the original? Good. Negative infinity to positive infinity. What would be its range?
2.
Good. What would be the inverse's domain?
Infinity.
2.
Good. And the range?
Negative infinity positive.
Good. Good. All right, I'm going to pass out homework.
Can I go to the bathroom?
Yes.